Jayambe, how are you all? I hope you all are great. Welcome back to my YouTube channel. My name is Prince Ranpara. I'm a PhD scholar in the Department of Chemical Engineering at the Indian Institute of the Technology, Ranpara. So in today's lecture, we are going to solve industrial numerical example which follows second order reaction kinetics, right? So let's get started. So remember that we are in today's lecture we are going to solve the industrial numerical example where we are going to keep all the operating parameters to be constant. We are going to use different reactor models. The different reactor models, right? CSTR, PFR, batch reactors, packed reactors. Okay. Now we need to identify how large volume of reactors do we require. We need to identify what will be the reaction time. We need to identify how much weight of the catalyst do we require in order to achieve the desired conversion, right? So let's understand that. So let's get started. So firstly here I'm selecting CSTR as the reactor model, right? So the reaction follows second order reaction kinetics where we have the given rate law has minus RA is equal to KCS square, where the given rate constant value has 250 liters per mole hour. Remember that we are keeping all the operating parameters to be constant, right? And we need to design by using the CSTR. We need to achieve the desired conversion of 90%, right? Now the question is, how large volume of CSTR do we require? The second question is, what will be the reaction time, okay, in order to achieve the desired conversion of 90%, right? So remember that how we design the volume of the CSTR. Recall the previous lectures, right? We have utilized the fundamental concept of the performance equation, right? So by using the fundamental concept of the performance equation, we have understood and we have designed the volume of the CSTR, right? So the first step is to write the performance equation of the CSTR, right? So the performance equation of the CSTR, which is given as V by Fa naught is equal to Xa divided by minus Ra is equal to T tau divided by Ca naught. So equation 1 represents the performance equation of CSTR, right? Now from this performance equation, we need to identify which values do we have in order to design the volume of the CSTR, right? So let's say from here we have the conversion value which is 0.90% conversion we need to achieve, right? Okay, we have the rate law value, right? Rate law has minus RA is equal to KCS square, right? We also have the initial molar flow rate which is 6 moles per hour. Okay, so from here we can make the subject as volume. Okay, so by comparing this both, we can make the subject as volume. Okay, so we'll get as volume of CSTR is equal to Fa naught into Xa divided by minus Ra. Okay, so now the numerator will remain as it is, right? Because it is constant. Initial molar flow rate is also constant. The conversion is also constant, right? So we are now replacing minus Ra with the given rate law. Minus Ra is equal to Kca square. So numerator will remain as constant. So is equal to numerator will remain constant. So Fa naught into Xa divided by Kca square, right? So now here, remember that this is exactly where the students get confused. Which form of Ca do we need to utilize? We have two forms of Ca. The first form of Ca is 0.1 Ca naught. Ca is equal to 0.1 Ca naught, right? And the second form of Ca is equal to Ca naught into 1 minus Xa. Okay, so remember that we need to always use whenever we are designing, whenever we are modifying the performance equation, the rate laws. Okay, whenever we are modifying the design equations, we'll always use second form of Ca, right? The second form of Ca, which is the fundamental relationship and also defines the conversion, right? So Ca is equal to Ca naught into 1 minus Xa, right? So here, which is equal to the numerator will remain as it is, which is Fa naught into Xa divided by K will remain as it is, and we are replacing Ca with its value. Ca is equal to Ca naught into 1 minus Xa, right? So here we have Ca square, so we are squaring the entire right hand side, right? So Ca naught square into 1 minus Xa whole square. Okay, so finally we have obtained the volume equation for the CSTR. So by using this equation 2, now we can design the volume of the CSTR required in order to achieve the desired conversion of 90%, right? Okay, so we have all the values. Just substitute all the values. If not, we have a 6 moles per hour. So volume of CSTR is equal to 6 moles per hour into Xa. Xa is 0.90 divided by K, which is 250 liters per mole hour, into Ca0 square, which is 0.4 moles per cubic decimeter whole square, into 1 minus Xa. Xa is 0.90 whole square, right? Okay, so we need to also remember that we need to also check the unit balance from, let's say, in numerator we have the presence of moles, in denominator we have the presence of moles, right? So this mole will go to the numerator, right? So which will become mole square, right? So which will become mole square. Okay, and from here we have the mole square, right? 0.4 mole per cubic decimeter whole square. So from this numerator, this mole will get cancelled off, mole square will get cancelled off, and from here this mole square will get cancel off, right? I hope you have understood. Okay, now in the numerator and denominator we have the presence of hours, right? So from the numerator and denominator the hours will get cancelled off, right? I hope you have understood. Okay, now let's say here in numerator we have the presence of liter, and here in denominator we have the presence of cubic decimeter whole square. Okay, cubic decimeter whole square, remember this. Okay, we have the presence of cubic decimeter whole square, right? So 1 liter equals to 1 cubic decimeter, right? So due to those reasons we can cancel off 1 liter is equal to 1 cubic decimeter from the numerator, and from denominator we can cancel off 1 cubic decimeter, right? So finally we will remain with the cubic decimeter, right, which will go to the numerator. Okay, so after solving this we'll get the answer as volume of the CSTR is equal to 13.5 cubic decimeter, right? Which means by keeping all the operating parameters to be constant, we are carrying the reaction in the CSTR. Right? The reaction follows second order reaction kinetics for the given rate law minus Ra is equal to K Cs square. Right? So by using the CSTR in order to achieve the desired conversion, we required 13.5 cubic decimeter volume of CSTR in order to achieve the desired conversion of 90%. Right? I hope you have understood. Okay. Now the second question is, okay, we have designed the volume of the CSTR, which comes out to be 13.5 cubic decimeter volume we required in order to achieve the 90% conversion. But now the second question is, how much reaction time do we require in order to achieve the same desired conversion of 90%, right? So let's understand that and let's calculate. So by using the fundamental concept of the space-time, we have calculated the reaction time. Okay, so we are using the fundamental concept of the space-time. The space-time is the ratio of volume to its volumetric flow rate. The volume of the reactor we have calculated, which comes out to be 13.5 cubic decimeter divided by the volumetric flow rate, which is 15 cubic decimeter per hour, right? So by solving this we'll get the answer as 0.9 hours, right? Remember, we need to also check the unit balance from the numerator and denominator. The decimeter cube will get cancelled off, and finally we are remaining with the hours, right? Okay, so which means we require 0.9 hours of reaction time in order to achieve the desired conversion of 90%, right? Which means by keeping all the operating parameters to be constant, we are carrying the reaction in the CSTR, and the reaction follows second order reaction kinetics for the given rate law, and then we required 13.5 cubic decimeter volume of CSTR and 0.9 hours of reaction time in order to achieve the desired conversion of 90%, right? I hope you have understood. Okay, so here we have understood the case of CSTR. Okay, so here we have completed the CSTR designing. Okay, now what if instead of CSTR, what if I use PFR? Then how large volume of PFR do we require in order to achieve the desired conversion of 90%, right? We need to calculate, we need to design. Okay, the second question is, if we are using the PFR, then how much reaction time do we require in order to achieve the desired conversion of 90%, right? So let's understand that. So let's say here in this part I will explain you the PFR, right? So we are now designing the PFR, right? So the first question is, how large volume of PFR do we require in order to achieve the desired conversion of 90%, right? So remember, first of all we'll always use the fundamental concept of the space-time. So by using the fundamental concept of the not the space-time, we'll always use the fundamental concept of the performance equation of PFR, right? So by understanding the performance equation of the PFR, by using the performance equation of the PFR, we can design the volume of the reactor required in order to achieve the desired conversion of 90%, right? Okay, so the first step is to write the performance equation of the PFR, which is given as B is equal to Fa naught integration of 0 to xa dx upon minus Ra, right? Okay, so here the minus Ra we can substitute with the given rate law. Minus Ra is equal to K Cs square, right? Therefore we can write as, now we need to solve this performance equation, right? So V is equal to Fa naught will remain as it is. So Fa naught integration of 0 to xa dxa upon minus Ra we are writing as K Cs square, right? Now again, this is exactly where most of the students will get confused. Which form of CA do we need to utilize, right? Remember, I will make you understand which form of CA do we need to utilize. So we'll always use, whenever we are designing, we are modifying the performance equation, the rate laws, we'll always try to use the second form of CA. The second form of CA is the fundamental relationship and also defines the conversion, right? So CA is equal to CA naught into 1 minus XA. Okay, so CA in the place of CA square, so we will write CA naught square into 1 minus XA whole square, right? So Fa naught, now remember that, so let's say is equal to Fa naught divided by K CA naught square, right? So we are taking K and CA naught square out of the integration, right? So why? Because K and CA naught square are the constant. The rate constant value is also constant and the CA naught value is also constant, right? So due to the constant terms, we can take out of the integral, right? So finally we'll get as Fa naught divided by K CA naught square. Integration of 0 to xa dxa upon 1 minus xa whole square. Now we need to solve the integral form, okay? We need to solve this integral form, right? So how we will solve? So let's understand that. So let's say here I am assuming that 1 minus xa is equal to y, right? Now in the second step, I'm differentiating on the both hand side. So differentiating the constant 1 will be 0, differentiation of constant will be 0, right? Minus will remain as it is, differentiation of xa will be dxa is equal to the differentiation of y will be dy, right? So I hope up to here you have understood. Now in the numerator we have dxa, right? So we require dxa, so we are transferring this negative sign on the right hand side, so we'll get the dxa is equal to minus dy, right? I hope up to here you have understood, right? Now we are solving this integral form, okay? So please understand carefully. V is equal to we are writing this term will remain as it is, Fa naught divided by K CA naught square, integration of 0 to xa, right? Okay, so integration from the lower limits to the upper limits, okay? I will make you understand the limits, okay? So let's say integration from lower limits to the upper limits, and dxa we are writing y minus dy, right? Dxa we are substituting by its value minus dy divided by 1 minus xa whole square, okay? So 1 minus xa is equal to y, right? So y whole square. So from here we have all the x terms, right, which we have converted to the y term, right? So we need to also make the changes in the limits, right? Here we have the in the form of x terms, right? But here we have in the form of y term. So limits we need to also change from the x term to y term, right? So due to those reasons, I have used the lower limit as y is equal to 1 and lower upper limits of y is equal to 1 minus xa. So how these lower limits and upper limits came, we need to also understand that, okay, which is very important, okay? So let's say here the lower limits, which is 0, which means the 0 indicates the 0% conversion, and xa upper limit xa represent the at any point of conversion, right? The fraction at any point of conversion, right? The conversion may be at 20%, 30%, 55%, 90%, or 100%, right? Which is the fraction of conversion, right? At any point of conversion in the reaction environment of the reactor, right? So let's say in the lower limit we have the conversion is equal to 0, which means at the start of the reaction, where at the initial start of the reaction, where we have the highest concentration of reactants present in the reaction environment, right? Which means reaction is not yet started, due to which the conversion is 0. Okay, so due to those reasons, we have 0 in the lower limits, right? So let's say if we put in this equation, if we put the conversion to be 0, then we will get as y is equal to 1. Okay, so due to those reasons, we can write the lower limits as y is equal to 1, which indicates the conversion to be 0 at the initial start of the reaction, right? I hope you have understood. Okay, I hope you have understood. Now the upper limits will understand. The XA represent the conversion at any point in the reaction environment of the reactor, right? So let's say y is equal to 1 minus XA also indicates the conversion XA, right? Y represent the fraction of conversion, right? At any point of the reaction environment in the reactor at any time. Okay, how much, what conversion we have achieved, okay, which is understand by the y is equal to 1 minus XA, right? So I hope you have understood the lower limits and the upper limits, right? So let's say y is equal to 1 minus XA, which means 1 which represent the 100% conversion, right, minus XA, which means the conversion which we have reached, and y represent the fraction of conversion which we have achieved, okay, in the reaction environment. I hope you have understood the upper limits, right? Now, so due to those reasons, we can write v is equal to fa naught divided by k ca naught square integration of y is equal to 1 to y is equal to 1 minus xa minus of dy by y square, right? Now, again, we need to solve this integral form, right? So let's say minus sign we can take out of the integral, right? So which is equal to minus of fa naught divided by k ca naught square, right? Integration of y is equal to 1 to y is equal to 1 minus xa, this integral will remain as it is. Now we are taking this y square to the numerator. From the denominator we are taking y squared into the numerator, so which will become y raised to minus 2 into dy, right? So integration of y is equal to 1 to y is equal to 1 minus xa, y raised to minus 2 dy, right? So integration of y raised to n dy will be y raised to n plus 1 divided by n plus 1, right? I hope you have understood, right? So here n is minus 2, right? So the solution of this integral, which is, so v is equal to, this entire term will remain as it is, so minus fa naught divided by k ca naught square, and the solution of this integral form is y raised to n, integration of y raised to n dy is y raised to n plus 1, y raised to n plus 1, and y raised upon n plus 1, right? So here n is minus 2, so the solution of this is y raised to minus 2 plus 1 divided by minus 2 plus 1. From the lower limits y is equal to 1 to upper limits y is equal to 1 minus x, right? So now for the solving, which is equal to, now let's say we'll get minus fa naught. Now this entire term will remain as it is, right? Minus fa naught divided by k ca naught whole square, right? In here we if we calculate minus 2 plus 1 will remain minus 1, right? So y raised to minus 1, and minus 2 plus 1 is minus 1, right? So from the numerator and denominator we can cancel off the negative sign, right? Okay, I hope up to here we understood, and limits will remain as it is. Okay, so finally we obtain as volume of PFR is equal to fa naught divided by k ca naught square, fa naught divided by k ca naught square into y raised to minus 1 will be 1 minus 1 divided by y raised to minus 1 will be 1 by y, right? So fa naught divided by k ca naught square into 1 by y, 1 divided by y, from the lower limits from y is equal to 1 to y is equal to 1 minus xa. Now we need to apply the limits, right? So this entire term will remain as it is, fa naught divided by k ca naught square. Now we are applying the upper limits minus lower limits, right? So 1 divided by 1 minus xa minus 1 divided by 1 minus 1 divided by 1, right? Now we need to take the LCM, right? So now see, which is equal to, now again this entire term will remain as it is, fa naught divided by k ca naught square, right? I hope you are understanding, right? So we are taking the LCM, right? So we are multiplying 1 minus xa to here, and we are multiplying 1 to here, and we are taking the LCM, right? So 1 will remain as it is, minus 1 minus 1 into 1 will become minus plus minus, so minus 1, and minus plus x, right? Divided by, we are multiplying both the denominators, right? So 1 minus xa, right? So from the numerator we have 1 minus 1, which means we get cancelled off, right? And we are remaining with the only xa in the numerator, and in denominator we are remaining with the 1 minus xa. So finally here we have derived the volume equation for the PFR. So volume of PFR is equal to Fa naught divided by K Ca naught square. So volume of PFR is equal to Fa naught divided by K Ca naught square into xa upon 1 minus xa upon 1 minus xa, right? So by using the equation 2, we can design the volume of the reactor. We can calculate how large volume of reactor do we require, okay, in order to achieve the desired conversion. Okay, so let's calculate that. We have all the values. Just substitute all the values, right? So volume of PFR is equal to Fa naught. We have Fa naught has 6 moles per hour, right? So 6 moles per hour. K we have as 250 liters per mole hour. Okay, in xa we have, okay, and Ca naught square we have as 0.4 mole per cubic decimeter, right, whole square, and the xa is 0.90 divided by 1 minus 0.90, right? Xa is 0.90. Okay, I hope up to here you have understood. Now just solve this and you will get the answer. Okay, we need to also cross verify with the units. From here we have moles in the numerator, and here also we have moles in the denominator of denominator, which will come to the numerator, right? So which will become mole square. So mole square will get cancelled off from the numerator, right? This mole square will get cancelled off in the numerator, and from the denominator this mole square will get cancelled off, right? I hope you have understood. The hours from the numerator and denominator will get cancelled off. So hours will from the numerator and denominator will also get cancelled off. Now we are remaining with the liter and cubic decimeter whole square, right? So 1 liter is equivalent to 1 cubic decimeter, right? So from the numerator, 1 liter is equal to 1 cubic decimeter will get cancelled off. Okay, so 1 liter is equal to 1 cubic decimeter, and cubic decimeter whole square will get cancelled off. Okay, and finally we will remain with the cubic decimeter. Okay, so after solving these, you will get the answer as volume of the PFR is equal to 1.35 cubic decimeter, which means by keeping all the operating parameters to be constant, we are carrying the reaction in the plug flow reactor, and the reaction follows second order reaction kinetics with the given rate law. Then by using the plug flow reactor, we required 1.35 cubic decimeter volume of the plug flow reactor in order to achieve the desired conversion of 90%, right? I hope you have understood, right? Okay, now the next question, which is, okay, we have designed the volume of the plug flow reactor, but how much time will it require in order to achieve the desired conversion of 90%, right? We need to calculate that. Okay, so here we will make the use of fundamental concept of the space-time, right? We'll use the fundamental concept of the space-time. So by using the fundamental concept of the space-time, we'll calculate the required reaction time, right? So the space-time is defined as the ratio of volume by its volumetric flow rate. Okay, so volume of the reactor, which comes out to be 1.35 cubic decimeter. So space-time of PFR is equal to volume of PFR, which is 1.35 cubic decimeter, divided by the volumetric flow rate, which is 15 cubic decimeter per hour, right? So from the 15 cubic decimeter per hour, from the numerator and denominator, the cubic decimeter will get cancelled off, and hour will get come into the numerator, right? So after solving this, we'll get the space time of PFR, which comes out to be 0.09 hours, which is 5.4 minutes, which means by using the PFR, we have kept all the operating parameters to be constant. Now we are carrying the reaction in the PFR, right? And the reaction follows second order reaction kinetics with the given rate law, right? So by using the PFR, we required 1.35 cubic decimeter volume of the PFR and 0.09 hours or 5.4 minutes of reaction time in order to achieve the desired conversion of 90%, right? I hope you have understood, right? So I request you to please make all the notes, right? So here we have completed the understanding of and the designing of the PFR for the second order reaction kinetics, right? Okay, now what if instead of CSTR or PFR, now what if I use batch reactor, then how large volume of batch reactor do I require? Okay, and what will be my reaction time in order to achieve the same design conversion of 90%, right? So let's understand that, right? So let's say now here in this part I will make you understand the batch reactor, designing of the batch reactors, right? Now let's say understand that in order to design the volume of the batch reactor, let's say we'll make the use of fundamental concept of the performance equation of the batch reactor, right? So the fundamental concept of the performance equation of the batch reactor, by using which by the performance equation of the batch reactor, by using the fundamental concept of the performance equation of the batch reactor, we can calculate the reaction time. How much time do the batch reactor required in order to achieve the desired conversion of 90%, right? Okay, so let's understand that. So first step is to write the performance equation of the batch reactor, right? So firstly we are writing the performance equation of the batch reactor, which is T is equal to Ca naught integration of 0 to xa dxa upon minus Ra, right? So equation 1 represent the performance equation of the batch reactor. So by using the fundamental concept of the performance equation of the batch reactor, we can calculate the required reaction time in order to achieve the desired conversion, okay, by using the batch reactor. So let's understand that and let's calculate. Okay, so let's say T is equal to Ca naught integration of 0 to xa dxa upon minus Ra, right? So minus Ra we are substituting by the given rate law, which is second order reaction kinetics, right? And the given rate law is minus Ra is equal to k Cs square. Okay, so we are substituting minus Ra with the k Cs square with the given rate law. Now again, this is exactly where the students will get confused, because which form of CA we need to utilize, first form of CA or second form of CA, right? So always remember, whenever we are modifying the performance equation or the rate laws, we'll always try to use second form of CA, right? The second form of CA, which is the fundamental relationship and also defines the conversion, right? So CA is equal to Ca naught into 1 minus Xa, right? So here we have Ca square. So we need to square on the both hand side. So Ca square is equal to Ca naught square into 1 minus Xa whole square, right? I hope you have understood. Okay, so is equal to Ca naught divided by K Ca naught whole square. So we are taking K and Ca naught whole square out of the integral, right? We are taking K and Ca naught whole square out of the integral, right? Because K and Ca naught whole square is constant, right? The rate constant value is constant and the initial concentration is also constant, right? Due to those reasons we can take out of the integration, right? Okay, now in the integral we remain with the integration of 0 to xa dxa upon 1 minus Xa whole square, right? I hope you understood. Okay, now let's say from the numerator and denominator we can cancel off the Ca naught, right? So Ca naught will get cancelled off from the numerator and denominator, right? So Ca naught we have cancelled off, right? So and we are remaining with the 1 upon K Ca naught integration of 0 to xa dxa upon 1 minus Xa whole square, right? Which means now we need to solve the integral form, right? Which means we need to solve this integral form, right? So you can see some similarity, right, in the case of batch reactor and as well as in the case of plug flow reactor. We have the same integral form of integration of 0 to xa dxa upon 1 minus Xa whole square, and here in the case of batch reactor we have the same integral form of integration 0 to xa dxa upon 1 minus Xa whole square, right? So remember that due to the same integral solution, right, we have the same integral solution as like of the PFR. Okay, so the solution of this integral will remain same as the PFR, right? So we will have the same solution of as like of the PFR, right? And where we have obtained the finally Xa upon 1 minus Xa has the solution Xa upon 1 minus Xa, right? I hope you have understood, right? So this solution of the integral form will remain same for the case of PFR as well as for the case of batch reactor, right? So due to those reasons we can write the integration of 0 to xa dxa upon 1 minus Xa whole square is equal to Xa upon 1 minus Xa, right? I hope you understood. Okay, so finally we can write T is equal to 1 divided by K Ca naught into Xa upon 1 minus Xa, right? So here we have derived the, here we have modified the, here we have derived the reaction time, equation, right? By using the equation 3, now we can calculate the reaction time required in order to achieve the desired conversion, right? We have all the values, just substitute all the values here, right? So 1 divided by K, which is 250 liters per mole hour, right? 250 liters per mole hour, divided by CA0, which is CA0 is equal to 0.4 moles per cubic decimeter, right? Into XA, which is 0.90, right? 0.90. Okay, so okay, 0.90 divided by 1 minus 0.90. Okay, now remember, we need to also cross verify the unit balance, right? So let's say from the numerator and denominator, moles will get cancelled off, and here we have presence of liter and in the numerator, and here in the denominator we have the cubic decimeter. So 1 liter is equal to the 1 cubic decimeter, right? So due to those reasons, the liter will get cancelled with the cubic decimeter. Okay, so finally we'll remain with the hour. Okay, I hope you understood. Okay, now after doing the calculation, we'll get the answer as T is equal to 0.09 hours of reaction time, which means we required, which means by keeping all the operating parameters to be constant, we are carrying the reaction in the batch reactor, right? And by using the batch reactor and the reaction follows second order reaction kinetics with the given rate law minus RA is equal to KCA square. Okay, we are carrying the reaction in the batch reactor, then we required 0.09 hours or 5.4 minutes of reaction time in order to achieve the desired conversion of 90%, right? I hope you have understood. Okay, so here we have completed the understanding for the reaction time, okay, in the case of batch reactor. But now the next question is, how large volume of batch reactor do we require in order to achieve the desired conversion of 90%, right? We need to understand that. So let's understand that and let's solve. Okay, so let's say the idea is I have make you understand in the previous lecture, I have make you understand the actual method to design the volume of the CSTR, right? If you want to recall, I request you to please watch the previous lectures, right? So let's say in order to design the volume of the CSTR, imagine that we have a certain volume of CSTR, right? In the certain volume of CSTR, in the reaction environment of the CSTR, will have the presence of reactants, right? Initial concentration of the reactants. So the concentration is defined as the ratio of initial number of moles with respect to the volume, right? So by based on this define, we can make the subject as volume, and we can design the volume of the actual volume of the actual batch reactor, right? Okay, I hope you have understood. So this is the actual method by which we can design the actual volume of the batch reactor, right? So concentration is defined as the ratio of number of moles divided by volume, right? Ca0 indicates the initial concentration and Na0 indicates the initial number of moles, right? Okay, so we can make the subject as volume V. So V is equal to Na0 divided by Ca0. So volume of the batch reactor is the ratio of initial number of moles present with respect to the initial concentration present in the reaction environment of the batch reactor, right? So from here we have two unknowns, which is volume of the batch reactor is unknown to us and initial number of mole is also unknown to us. Okay, we only know Ca0, initial concentration, which is 0.4 moles per cubic decimeter. Okay, so now the question is how we can calculate the initial number of moles present in the reaction environment of the reactor, right? So let's say initial number of moles is the product of the charge time with the molar flow rates, right? Initial number of moles is the product of the charge time into molar flow rates. Okay, now here I am assuming that the charge time is equal to the reaction time. The charge time is equal to the reaction time is equal to 0.09 hours, right? So is it always mandatory that the charge time is equal to the reaction time? So the answer is no, it is not mandatory that the charge time is equal to the reaction time, right? Why? Because the charge time depends upon the availability of the good operating pump systems, right? Okay, so initially for our calculation I'm assuming that the charge time is equal to the reaction time. Okay, so due to those reasons we can write the N0 is equal to charge time of 0.09 hours into the initial molar flow rate, which is 6 moles per hour. So from numerator and denominator, the hours will get cancelled off and will remain with the moles. So after calculating, we'll get the answer is 0.54 moles, which means we have here we have calculated the initial number of moles present in the volume of the reactor, which comes out to be 0.54 moles, right? So now we have the value of initial number of moles, and we also have the value of Ca naught. So by taking the ratios of initial number of moles and the concentration, we can finally design the volume of reactor we required, right? So let's calculate that. Okay, so volume of the batch reactor is equal to initial number of moles, which is 0.54 moles, divided by initial concentration, which is 0.4 moles per cubic decimeter, right? From the, we need to also cross verify the unit balance, right? So from the numerator and denominator, the moles will get cancelled off, right? So after solving this, 0.54 divided by 0.4, you will get the answer of 1.35 cubic decimeter, which means by keeping all the operating parameters to be constant, okay, we are carrying the reaction in the batch reactor, right? And the reaction follows second order reaction kinetics with the given rate law minus Ra is equal to Kc square, right? The reaction, we are carrying the reaction in the batch reactor, and in order to achieve the desired conversion of 90%, we required 0.09 hours or 5.4 minutes of reaction time and 1.35 cubic decimeter volume of the batch reactor in order to achieve the desired conversion of 90%, right? Okay, I hope you have understood. So finally, here we have completed the designing of the batch reactors for the second order reaction kinetics, right? So I request you to please make all the notes, okay? So I request you to please make all the notes, okay? So I hope you have made the notes, right? Now let's say we will solve. Now what if instead of CSTR, plug flow reactor or batch reactor, what if now if we select packed bed reactor, right? Then how large volume of packed bed reactor do we require? What will be the reaction time in order to achieve the same desired conversion of 90%, right? So we need to understand that, okay? So let's say now we are selecting the packed bed reactor as the reactor model, right? We are keeping, again remember, we are keeping all the operating parameters to be constant. We are solving for the second order reaction kinetics for the given rate flow minus Ra is equal to K Cs square, where the rate constant value is K is equal to 250 dm raised to 6 divided by moles per kg hour, right? Okay, so let's say here now we are designing the packed bed reactor right? Which means the rate constant unit has changed, okay? So let's say the rate constant unit is 250 dm cube whole square divided by mole per kg catalyst hour, okay? So first of all, in order to design any reactor, the first step is to write the performance equation of the reactor, right? So we are going to utilize the fundamental concept of the performance equation for the packed bed reactor in order to design how much weight of the catalyst do we require in order to achieve the desired conversion of 90%, right? So let's say here the first equation represents the performance equation of packed bed reactor, which is W is equal to Fa naught integration of 0 to xa dxa upon minus Ra, right? Now in the place of minus Ra, we are going to substitute with the given rate law. Minus Ra is equal to Kca square. So Fa naught integration of 0 to xa dxa upon minus Ra, right? Dxa upon minus Ra, we are substituting by Kca square, right? Now again remember, the students are getting confused here at which form of Ca do we utilize, okay, in order to derive the performance equation, right? So always remember, we will utilize the second form of Ca, which is indicated as Ca is equal to Ca naught into 1 minus Xa, right? So remember, always remember, we will use this second form of Ca in order to modify the performance equation, right? Always remember. So we are using Ca is equal to Ca naught into 1 minus Xa, right? So here we have Ca square, right? So let's say we are squaring both the sides. So Ca square is equal to Ca naught square into 1 minus Xa whole square, right? So which is equal to Fa naught will remain as it is because Fa naught is constant. We are taking K and Ca naught square out of the integration, right? Why? Because K and Ca naught square are the constant, right? The rate constant value is constant and Ca naught is also constant, right? So due to those reasons, we are taking K and Ca naught out of the integration, right? So we remain with the integral form, which is integration of 0 to xa dxa upon 1 minus xa whole square, right? I hope you have understood. Okay, so here we are going to utilize the second form of Ca, right? Now we need to solve this integral form, right, in order to modify the weight equation, right? So let's say the solution of this is same as the PFR and the batch reactors, right? Okay, so previously only I explained you how we are solving this integral form, right? If you want to recall, I request you to please watch some few minutes before, okay, where I have made you explain how we solve this integral form, right? So the solution of this integral form, which comes out to be xa upon 1 minus xa, right? So integration of 0 to xa dxa upon 1 minus xa is equal to xa upon 1 minus xa is the solution, right? So finally we have obtained the solution of this integral form, right? Now we will substitute that. So w is equal to Fn, this entire term will remain as it is, so Fn naught divided by Kc naught square into xa upon 1 minus xa. Now we have obtained the weight equation, right? So by now we have all the values, so just substitute all the values. So Fn naught is given as 6 moles per hour divided by K, which is 250 dm raised to 6 divided by mole per kg hour, right? Dm cube whole square is dm6 divided by mole per kg catalyst hour. Ca naught is equal to 0.4 moles per cubic decimeter, right? So here we have the Ca naught square, so 0.4 moles per cubic decimeter whole square into xa upon 1 minus xa, right? So xa is 0.90 upon 1 minus 0.90, right? Now you need to just solve, right? Before that, always remember we need to see the unit balance, right? So let's say in numerator we have moles and in denominator we have moles. So these moles will come to the numerator, right? So it will become mole square. So mole square from the numerator will get cancelled off with the denominator mole square, right? Okay. So here we have dm raised to 6, right? So here dm cube whole square, so it will become dm6, right? So from this numerator and denominator, this dm6 will also get cancelled off, right? Now the hour from the numerator and denominator will get cancelled off, so we'll finally remain with the kg. Okay, so this kg will come into the numerator. So after solving this, you will get the answer as weight of the catalyst is equal to 1.35 kg, right? Which means by keeping all the operating parameters to be constant, we are carrying out the reaction in the packed bed reactor, right? The reaction follows second order reaction kinetics with the given rate flow minus Re is equal to Kcs square, right? So by using the packed bed reactor we required 1.35 kg weight of the catalyst in order to achieve 90% conversion, right? I hope you have understood, right? So I request you to please make this note. Okay, now we know how much weight. The question was how much amount of weight do we require in order to achieve the 90% conversion, right? We have calculated, right? Now the next question which arises into our mind is, how large volume of packed bed reactor do we require in order to achieve the desired conversion of 90%, right? So let's say in the previous lectures I have made you explain in a very clear and systematic manner the actual method to design the volume of the packed bed reactor. If you want to recall, I request you to please watch the previous lecture, right? So the actual method to design the volume of the packed bed reactor is the ratio of weight of the catalyst divided by its bulk density. The bulk density here, the VBR represent the volume of the packed bed reactor, W represent the catalyst weight, and rho B represent the bulk density. Bulk density is the ratio of weight of the catalyst by its total volume occupied by the solid catalyst, right? Okay, so let's say here we are assuming weight of the here we are assuming then bulk density of the solid catalyst to be 700 kg per meter cube. Okay, so remember, so always it is mandatory that the bulk density will be equalized to 700 kg per meter cube. So the answer is no. So okay, it is not mandatory that the bulk density of the catalyst bed will be always equal to 700 kg per meter cube. It is not mandatory, right? The bulk density may vary. Okay, so let's say for our initial calculations, for our initial designing the volume of the packed bed reactor, I am assuming the bulk density of the catalyst bed, which is equalized to the 700 kg per meter cube. Okay, I hope you have understood, right? So let's say by assuming this bulk density of 700 kg per meter cube, let's say now we have the bulk density, we have the weight of the catalyst. Now we can finally calculate the volume of the packed bed reactor. So let's calculate. So volume of the packed bed reactor is equal to, the weight of the catalyst is 1.35 kg, right? So 1.35 kg divided by its bulk density 700 kg per meter cube. So from the numerator and denominator, the kg will get cancelled off and will finally remain with the meter cube, right? So if we solve this, we'll get the answer as volume of packed bed reactor is equal to 0.00193 meter cube. So 1 meter cube equals to 1000 decimeter cube, right? 1000 cubic decimeter. So here, if we convert this 0.00193 meter cube into this cubic decimeter, which the answer will come as 1.93 cubic decimeter, which is equivalent to 2 cubic decimeter, right? 2 liters volume. Okay, which means by keeping all the operating parameters to be constant, we are using packed bed reactor and we are carrying out the reaction in the packed bed reactor. The reaction follows second order reaction kinetics with the given weight law minus Ra is equal to KCS square. So in order to achieve the 90% conversion by using the packed bed reactor, we required 2 cubic decimeter volume of the packed bed reactor in order to achieve the desired conversion of 90%, and we required 1.35 kg weight of the solid catalyst in order to achieve the 90% conversion by using the packed bed reactor model, right? I hope you have understood, right? Okay, now let's say we have identified how much weight of the catalyst we require in order to achieve the 90% conversion. We have also identified how large volume of packed bed reactor we required in order to achieve the desired conversion of 90% by using the packed bed reactor. Okay, but now how much reaction time will be required in order to achieve the same desired conversion of 90%, right? So we'll calculate that. So the reaction time, which is equalized to the space time, right? Which means now we are going to use the fundamental concept of the space time. The space time is the ratio of volume to its volumetric flow rate. The volume of the reactor, packed bed reactor, which comes out to be 2 cubic decimeter, and the volumetric flow rate is 15 cubic decimeter per hour, right? So from the numerator and denominator, the cubic decimeter will get cancelled off. So finally, we will remain with the tau PBR, which is equalized to 0.1333 hours, right? Which means the space time of the packed bed reactor is 0.1333 hours, which is equalized to 7.998 minutes, which means 8 minutes of reaction time we required, okay, for the packed bed reactor. Which means by keeping all the operating parameters to be constant, we are carrying second order reaction kinetics in the packed bed reactor. So we required 1.35 kg weight of the catalyst, we required 2 cubic decimeter volume of the packed bed reactor, and we required 8 minutes of the reaction time in order to achieve the same desired conversion of 90% by using the packed bed reactor, right? I hope you have understood, right, up to here. Okay, so finally here we have completed the designing of the packed bed reactor, right, for the second order reaction kinetics, right? I hope you have understood, right? So I request you to please make all the notes, right? Now let's say we will delve more deeper into the understanding of, let's say, now what if the bulk density changes? What if the bulk density gets higher? What if the bulk density gets lower? So how does the change in bulk density will affect to the reactor volume, to the reaction time, space time, to the weight of the catalyst, or let's say the void fraction, pressure drop, and the packing tightness? So let's understand that, right? So let's say, remember, here we are keeping the weight of the catalyst to be same, right? For each and every case, we keep the weight of the catalyst as 1.35 kg catalyst, right? Okay, because the weight of the catalyst we have calculated by using the performance equation of the Beckett reactor, right? So due to those reasons, we'll keep weight of the catalyst to be constant. Okay, now what if we change the bulk density? So what if, so we are here trying to see the effect of change in bulk density over the volume of the Beckett reactor, the void fraction, pressure drop, and packing tightness, right? So let's understand that. So let's say in the first case where we have assumed in the first case where we have assumed 7 kg per meter cube has a bulk density, right, which is our standard case. So let's say we obtain the volume of Beckett reactor to be 2 cubic decimeter, right, and the volume fraction, and we have seen the effect of volume fraction, pressure drop, and packing tightness, right? So let's say now what if from the if I increase my bulk density from 700 to 1000 and 2595 kg per meter cube, right? So by increasing the bulk density from 700,000 to 2595, how does the increase in the bulk density will affect to the volume of the Beckett reactor, to the void fraction, the pressure drop, and the packing tightness? So let's understand that, right? So let's say if I increase my bulk density from 700 to 1000 to 2595, you can say that the volume of the Beckett reactor is decreased, right? Which means we are tightly packing, right? Which means the void fraction in the catalyst bed is decreasing, right? Which means the void fraction, which means the space between the solid particles decreases, right? Which means we are tightly packing the solid catalyst into the reactor, right? So if the bulk density increases, you can see there will be a decrease in the required volume of the Beckett reactor, design volume of the Beckett reactor, due to which, because the void fraction is decreasing, right? The void space between the solid particles is decreased, right? Okay, due to which there are chances, due to which there will be due to which the pressure drop will increase, right? Due to the tightness in the packing, right? We are tightly packing the solid catalyst into the reactor. Okay, I hope you have understood now. Okay, now the another case where what if I reduce the bulk density, if we reduce the bulk density from 700 to 500, 121, right? So what will happen? So now we are trying to understand the effect of decrease in bulk density from 700 to 500, 121. So how does the decrease in bulk density will affect the other operating parameters, right? Require variables like volume of the Beckett reactor, the void fraction, the pressure drop, and the packing tightness, right? So let's say now if we decrease the bulk density from 700 to 500, 121, you can see that the design volume of the Beckett reactor is increased from 2 to 2.7, 13.5, and 60.43, which means by decreasing the bulk density, which means the volume of the reactor is increased, right? Which means we required larger volume of the reactor in order to accommodate all the weight of the catalyst, right? 1.35 kg weight of the catalyst, right? Which means by decreasing the bulk density from 700 to 500, 121, which means the void fraction is increased, right? The void fraction is increasing, which means the void space between the solid particles is increasing, right? The void space between the solid particles is increasing, right? So due to increase in the void space between the solid particles, we will observe there will be a decrease in the pressure drop. Okay, there will be a decrease in the pressure drop, and the packing tightness will decrease. The packing tightness will decrease, which means now the bed is becoming a lesser tight, right? Which means the packing tightness of the catalyst bed decreases due to decrease in the bulk density, right? I hope you have understood. Okay, so I request you to please make all the notes. Okay, so in order to conclude, if the bulk density increases, the volume of the Beckett reactor decreases. So due to the decrease in the volume of the Beckett reactor, which means the void fraction also, the void fraction of the solid catalyst particle decrease, right? Due to which the void space between the solid particle is decreased, which result into the increase in the pressure drop, and the packing tightness increases. By increasing the bulk density, which means we require larger reactor volume in order to accommodate the solid catalyst, right? Due to increase in the void space between the solid particles, right? Which will result into the decrease in the pressure drop and in decrease in the tightness of the packing, right? I hope you understood, right? So in order to conclude this lecture, in today's lecture we have kept all the operating parameters to be constant, right? And we have carried out the reaction which follows second order reaction kinetics. So here we have used different reactor models. The reactor models like CSTR, PFR, plug flow reactor, batch reactors, and big bed reactors, right? And we are trying to analyze how large volume of reactors do we require. We are trying to analyze how much reaction time do we require. We are trying to analyze how much amount of weight of catalyst do we require in order to achieve the desired conversion of 90%, right? Okay, so I hope you have understood. Okay, so I request you. So here in today's lecture we have completed the entire industrial numerical example for which follows second order reaction kinetics, right? So I hope you understood, right? So now in the upcoming lectures I will make a detailed comparative analysis between the I will make engineering conclusion in between the CSTR, PFR, batch reactors and packed bed reactors, right? And we'll delve more deeper into the fundamental understanding of the second order reaction kinetics in the upcoming lecture, right? So until then, stay focused, keep learning and stay curious. Thank you for watching my video. Jai Ambe.